In this video, I want to do a slightly harder example of how we might use proof by induction to prove divisibility of certain expressions. So in particular, we're going to take this expression un here and show that this is divisible by 7 for all n greater or equal to 2. So starting with our base case, and it's worth being careful here, is when n is 2, because we're asked to show for all n greater or equal to 2. And it's worth just checking that when n is 1, this is in fact not even true that this is divisible by 7, because when n equals 1, u1 is equal to negative 6 to the power of minus 1 plus 8 squared minus 2, and this is not even an integer. So it definitely isn't divisible by 6. Okay, so let's check our base case. u2 equals negative 6, 2 times 2 minus 3 is 1, plus 8 to the power of 3 subtract 2. Well, that is 504, which is 72 times 7, so it definitely is divisible by 7. And now we want to do our inductive step. So we are going to assume true when n is equal to k. Well, what is that we're assuming? We're assuming that uk, which is equal to negative 6 to the power of 2k minus 3 plus 8k plus 1 subtract 2, is divisible by 7, and it might help you to say that is equal to some 7m. So we're assuming that u to k is divisible by 7. And what do we want to show? Well, we want to show if this assumption is true, then it is also true when n equals k plus 1. So we want to show true when n is equal to k plus 1. So i.e. we want to show that uk plus 1, which is equal to negative 6 to the power of 2 lots of k plus 1, subtract 3, plus 8k plus 1 plus 1 minus 2 is divisible by 7. Okay, so let's start with uk plus 1, and we want to show that this is divisible by 7 given our assumption. So uk plus 1 is equal to negative 6 to the power of 2k plus 2 minus 3, just expanding out that bracket, plus 8 to the k plus 2 subtract 2. And we can use a similar idea as before, and it doesn't really matter whether we take minus 6 to the 2k minus 3 in our assumption, or 8 to the k plus 1, or even the minus 2. We're just going to make one of these things the subject. So I'm going to make negative 6 to the 2k minus 3 the subject. So what is that equal to? Well, that is equal to uk, subtract 8 to the k plus 1, add 2. And we can make this substitution into here. Well, how can we do this? Well, take the first term here, and noticing that this is equal to minus 6 to the 2k plus minus 3 times by minus 6 squared plus 8 to the k plus 2 subtract 2, we can now substitute in for our negative 6 to the 2k minus 3, so we get uk minus 8 to the power of k plus 1 plus 2, all times by negative 6 squared, which is 36, plus 8 to the k plus 2, subtract 2. And let's expand this out. So we get 36 lots of UK minus 36 lots of 8 to the k plus 1 plus 72, which is 2 times 36, plus 8 to the k plus 2, subtract 2, which is 36 u to the k, subtract plus 70, which is the 72, subtract 2, and let's take a factor of 8 to the k plus 1 from those remaining two terms. Well, we get a negative 36 here, and here we just need an 8. So we have 8 to the k plus 1 multiplied by 8 is 8 to the k plus 2. So this is 36 UK plus 70 plus, well, negative 36 plus 8 is negative 28. So negative 28 lots of 8 to the k plus 1. And we can see here that each of these terms are multiples of 7. This is a multiple of 7 because 7 divides 28. This is a multiple of 7 because 7 divides 70. And this is a multiple of 7 because of our inductive hypothesis, because our assumption was that UK is divisible by 7. And if that's not totally clear, we can let u to the k equal 7m, as we suggested before, and make that substitution. So this is equal to 36 times 7m plus 70 minus 28 lots of 8 to the k plus 1. And then we can take a factor of 7, and we can be absolutely convinced that this is a multiple of 7. It's worth just pointing out here that this is only an integer if 8 to the k plus 1 is an integer. But 8 to the k plus 1 is an integer whenever k plus 1 is greater or equal to 0, i.e. k is greater or equal to minus 1. But because our base case was when n equals 2, then we know we're only interested here in k's that are greater or equal to 2. So 8 to the k plus 1 definitely is an integer here. So what have we done? Well, we have shown that un is divisible by 7 when n equals 2. And if un is divisible by 7 when n equals k, un is also divisible by 7 when n equals k plus 1. And so un is divisible by 7 for all integer n where n is greater or equal to 2.